Welcome back to ECE 441A 541A. In this short or brief segment that I'm entitling Velocity Gain Constant and Steady State Air, I want to derive this equation or expression for the velocity gain constant, and I will do that in the process of relating that to the steady state air when we actually have a type 1 system and a ramp applied to our stable closed loop system configuration. What we want to do then is derive case of V, which is equal to the limit as s goes to 0 of s g of s, and we're assuming that g of s is a type 1 system. Or another way of saying that is g of s contains a pure integrator, or many different ways of thinking about a type 1 system, or it has an s factor in its denominator, a linear factor that only contains s and no constant term. That's one of the assumptions that we will be making in this derivation, that we are starting with a plant, g of s, that's a type 1 system. A second assumption that we are making is we are going to go ahead and assume that we have unity output feedback. And we're assuming that that feedback is negative. Our block diagram then consists of our type 1 system with feedback around that. We have a reference input R. We're comparing that reference input to the output directly, Y. And we also are very interested in the behavior of the air signal E that actually drives this plant in the closed loop configuration. For completeness, let's go ahead and derive that expression for the air signal E. That's just the output of that summing junction, which must equal the input to the summing junction, which is R of S, the reference, minus Y of S. But we can start to simplify things if we rewrite the output Y as G of S, E of S. And now we can collect our E of S terms on the left. We have 1, and we have plus G of S. All of those are scaling E of S. And all we have left on the right-hand side is R of S. And that allows us then to write an expression for the air signal E of S in terms of the plant and the reference input R of S. Our transfer function then between the reference input R and the air signal E is 1 over 1 plus G when we have negative unity output feedback. What we want to do is look at or examine this air in the time domain. This is the frequency domain expression for the air signal. We want to look at the time domain expression for the air as time goes to infinity, which infinity could just be 5 time constants, when the reference input signal R of t is actually a unit ramp. Because we know if G is a type 1 system, we have 0 air due to a constant input. So let's look at some reference input signal that will generate a non-zero air signal. So let R of t be, and now just for ease of discussion, let's let r of t be a unit ramp. We're now saying that r of t is simply equal to 1 times t for non-negative values of t, and it's 0 before t gets to 0. Or we will need to find what r of t is in the frequency domain, and Laplace transforming little r of t produces then capital R of s equaling 1 over s squared. We will make the following assumption. We will assume that this closed loop system is in fact stable. If it's not, then we won't have a well-behaved error signal, and this will all not be valid. So let's now just assume that, or state that, if the closed loop system is stable, let's find an expression for this steady state error. The steady state error is a time domain quantity, and we want to know what happens when we finally reach steady state, which is a limiting condition on little e as a function of time, but by means of the final value theorem, that's simply the limit as s goes to 0 of s capital E of s, where E of s is our frequency domain expression that we derived above. This relationship then comes to us from the final value theorem. We can then say that we're interested in the limit as s goes to 0 of s, can't forget that, so maybe I should give myself a little bit more space, s, e of s, but e of s is 1 over 1 plus g of s, r of s, but r of s for a unit ramp is 1 over s squared. This s in front is going to cancel one of those s's on the far right, and we now have the limit as s goes to 0 of 1 over 1 plus g of s times 1 over s. But that's simply if we distribute that s across both terms in the denominator. We now have the limit as s goes to 0 of 1 over s plus s g of s. That's our expression for little e sub ss, or the limit as time goes to infinity on our error signal e of t. There's nothing involving s in the numerator, which means that we can look at this limit strictly in the denominator, and we can now push that limit downstairs, and we now have the limit of the quantity s plus s g of s. This is now two terms. The first piece of that denominator, s, as s goes to 0, simply vanishes. And so now we're left with 0 plus the limit as s goes to 0 of s g of s, but that will just be some number because we've assumed g of s is a type 1 system, which means that s in the numerator is going to cancel the lone s in the denominator because of the type 1 system, and it's convention to simply say that that expression is 1 over some gain, and we call that gain the velocity gain because this ramp signal is like a velocity signal, where k sub v equals the limit as s goes to 0 of s g of s, simply equating expressions in the denominator, and that's true when g of s is a type 1 system. We've then shown that for a type 1 system and a closed loop unity output feedback configuration, the steady state error due to a unit ramp is 1 over k sub v, where k sub v, so there's the relationship between the steady state error and this velocity gain constant, where k sub v is now defined to be the limit as s goes to 0 of s g of s. And that's what we set out to show.